Hi everyone, and welcome to this series of electrical B7 power system engineering exam, PO exam. And this is a question from after the pandemic for December 2021. And this is transformer question number 3, and it has 3 different parts, somehow related to each other. Okay, so without overdue, let's start with the first part because this is a lengthy question. So in the first part of this question, it says here a single phase 20 kVA distribution transformer used to step down the voltage from 7200 to 240 volt. Find the actual value of the leakage reactance in ohms if the per unit value is 0.07, and we want to find the actual leakage reactance refer to the high voltage side and refer to the low voltage side. Okay, so here's given to per unit as per unit 0.07. This is unitless. Now we need to find basically the actual value. And the Z ohm, the actual value is equal to Z per unit times Z base. Now the per unit will be the same either to the high voltage or to the low voltage side. It doesn't really matter. So what we want to find here is to find Z base. And you will have two Z base, one referred to the high voltage and one referred to the low voltage. So what is the formula for Z base? So Z base equal to the voltage base square divided by S base. Now, the base values here is the rated value, okay? Now, since I want to find first the Z base for the high voltage side is equal to the voltage at the high voltage side, 7200 square, divided by S base, which is the rated value of the of your transform, which is 20 times 10 to power 3, and this will give me 2592 ohms. Okay, so from this we can find the Z in ohms referred to the high voltage side, which is equal to the 2592 times the 0.07, and this will give me 181.44 ohm. Okay, now let's find Z base refer to the low voltage side. It's the same formula, but all we need to change is the voltage because now are moving from the high voltage to the low voltage. So it's basically 240 square divided by 20 times 10 to the power 3. And this will give me 2.88 ohm. And hence Z ohm from the low voltage side, it is the 0.088 times 0.07, and this will give me a value equal to 0.2016. Okay, so these are the two values. This is from the high voltage and here from the low voltage. And here I want to stress on something very important because there is a typo in the second part. You will see here that whenever you find the values of the resistance or the impedances referred to the high voltage side, its value is much larger than referred to the low voltage side. And the resistance and the impedance at the low voltage side is much smaller than the impedance and the high voltage side. And the reason for that, because at the low voltage side, the current is extremely high. So the I square R loss, you want to balance the losses in the primary and in the secondary so the resistance in the low voltage side is always much less than the resistance in the high voltage side. Keep this information in mind as we go to the second part. Now, in the second part, we need to calculate the voltage regulation. But before that, I'd like to make some analogy, something to have some feeling of the question. This question I solved before. So this is the question before this one. I think this is December 2021 or something like that, or 2020. Okay. And this is the question of this exam. Now here, the value of R1, R2, X1, and X2 in that question both refer to the high voltage side. Okay, so both of them R1 and R2, X1 and X2, and plus also all these were referred to the high voltage side. Now, when they are referred to the high side, you see that R1 and R2 are comparable, same order of magnitude. X1 and X2 are basically at the same order of magnitude. In this question, no. You see that R1 is 35 ohms, R2 is 0.05. X1 is 90 ohm, X2 is 0.11 ohm. So they are not in the same order of magnitude, okay? And that's when they are taken at two different, each one taken at two different sides, then basically that what happens. Okay, as I mentioned, the resistance impedance at the low voltage side is much less than the impedance at the high voltage side. So this is something that's a fundamental difference between this question, which the values are already having one common referral side, but in this question, no, part of it refer to the primary and part it refer to the secondary. Just I want to make this note before we proceed. Okay, so here is a similar transformer that the one we did for the per unit, but this one is basically step up. So this is the primary side and this is the secondary side, okay? This is the primary and this is the secondary. Now, this becomes a step up instead of a step down because the previous one, in the previous question, it was 7,200 by 240. So this is step down transformer. Now this is a step up, and any transformer can be step up or step down depending where you inject your source or from where the supply is applied and where is the load is connected. Okay. Now has the following equivalent impedance. R1 and R2, X1, X2, RC, and XM. And say R1, X1, RC, and XM are referred to the primary. Refer to the primary, it means refer to the low voltage side in this transformer. R2 and X2 refer to the secondary, which is the high voltage side. Now, when you look carefully to the values, this is contradict the fundamentals of the transformer. So when you say that R1, X1, so R1 and X1, which has higher value, these are referred to the primary or to the low voltage side, while the high voltage side, basically you have the smaller value, this is the opposite. So basically this is wrong. This has to be the secondary, and this has to be the primary to be consistent with the fundamentals of the transformer. So that is the true values. Now we need to use the approximate equivalent circuit to estimate the transformer voltage regulations. At what condition? When we have rated unit power factor at rated secondary voltage. So when you have the rated power supplied at basically unity power factor, what is the voltage regulation? I will solve these questions using the two circuits. The one that is referred to the high voltage side or to the primary, and the one referred to the secondary. Okay, so I will start with circuit that referred to the basically to the secondary. Sorry, to the primary. Sorry, to the primary. This is to the primary. I will start by referring everything to the primary. So let me draw the original circuit. So this is R1, X1, RC, XM. And here you have, so this is R1, X1, R2, X2. Now, since everything is referred to the primary, then this will be AVS, and this is IS over A. This is the V primary, and this is the I primary, because I'm referring everything to the primary. So the secondary multiplied by the ratio. The voltage you multiply by A, the current you divide by A. Okay, so the voltage, now what is A? Now, this is basically a step up, so it's primary over secondary, so it's 240 divided by 7 to 100, which is make it equal to 1 over 30. So it means that AVS 1 over 30 times the 7 to 100 would just make it 240. 244. Now let's go to these parameters. Now R2 and X2 are referred to the primary actually, so we keep them as they are. We don't change their value. 0.05 and J 0.11. Now, R1 and X1, these are the ones that we multiply them with A square because these are referred to the secondary and we want to refer them to the primary. So everything has to be multiplied by A square. So your R1 will equal to A square R1, which will make it equal to A square, which is 1 over 30 square times R1, which is 35. And this will give me 0.039 ohms. X1, again, A square X1. And this will give me a value of J 0.1. Then you will have also RC and XM. Again, I need to multiply them by the A square. So your RC will be equal to 83.3 ohm, and XM will be J 55.5 ohm. So that is your model. Now, when you did this, you will find that R1 and X1 are the same order of magnitude as R2 and X2. This will give you an impression or assurance that your process is correct. When you refer both the values to one side, they should be at the same order of magnitude. Now, what I will do, I will move this branch here. So you will have the approximate model. This is what he asked you to do. So basically, we will have, this is your RC and XM. You will have the R equivalent and the X equivalent. Your R equivalent is basically equal to 0.089 ohm because I am adding the 0.039 plus the 0.05, and the X equivalent will be equal to J 0.21, and here is the 240 volt, which is the AVS. Now I need to find VP, the primary voltage here. So I need to find the current. Okay, so the current I in the secondary is equal to 20, the rated value, divided by the voltage, the actual voltage of the secondary, which is the 7,200, and this will give you 2.78 amps. The angle, of course, will be 0 because it's a unity power factor. Now, this current is not IS, it should be IS over A, and A is equal to 130, so your IS over A will be equal to total current of 83.3 amps. Now find VP. VP is basically just a simple KVL, is 240 angle of 0 plus 83.3 angle of 0 times the impedance, which is 0.089 plus J 0.21, and this will give me a total voltage equal to 248.04 angle of 4.05. Now, what is the voltage regulation? Voltage regulation equal to V at no load minus V at full load divided by V at full load. Where at the secondary side, so the voltage regulation is equal to basically the secondary side. Now, the V full load is basically the voltage at the rated condition. This is at the rated condition. That was the voltage. So this will be minus 240 and this is 240. Now, what is the voltage at no load? The voltage at no load, imagine the current I is equal to 0, no current. So the voltage at the secondary now will be the voltage at the primary side because there is no voltage drop, which is equal to the 248.04, everything times 100, and this gives me a total equal to 3.35%. So that is the voltage regulation. Now, to make things even clearer to you, let's find everything but now referred to secondary. As I pointed out, there is a mistake here. So these referred to the secondary and these refers to the primary. So anything referred to the secondary, I don't change it. I keep it as it is. So let me again draw the exact model, and then we will go from there and we will go to the approximate model by moving the primary branch to the secondary branch and adding them in series. Okay, now everything referred to the secondary, it means the voltage here now will be Vs only, which is the 7,200. So this is the voltage that I will be working with. And here I will use Is as it is. Is, we already calculate that, which is basically is equal to 2.78 amp. So this is 2.78 angle of 0 actually. Okay, now R1 stays as it is, 35. X1 90, J90, RC stays as it is, 75 kilo ohm, and XM is J50 kilo ohm. Okay, now I need to change these values who were taken, refer to the primary, and then I want to refer them to the secondary. So what we do, we divide by a square. So basically here your R2 will be R2 divided by a square. And this will be equal to your R2 value, which is 0.05 divided by a square. Then you multiply by 900, which is 1 over a square. With the division, it get inverted. So this gives me 45 ohm. And x2 will equal to x2 over a square, and this will give me a value of 0.11 times 900, and this will give me 99 ohm. Again, look to this value when I refer it to the secondary, and you look to this value, they are exactly, or they are at the same order of magnitude. Now I am ready to draw the model. So my model now would be like this. So this stays as it is, no change here, RC and XM. So this is basically 75 kilo, J50 kilo. Now your R equivalent, you add the 45 plus the 30. So this is 80. Basically, this is 80 ohm. And this is J, which is 99 plus 90, J189. The voltage here is 7,200. The current here is 2.78 angle of 0. Now the voltage here will be V primary over A. Okay, and the current here will be AI primary, because now this is referred to what? To the others. Okay, very good. So we have everything. So VP over A is equal the same thing, 7,200 angle of 0 plus 2.78 angle of 0 times 80 plus J189. And when you do that, you will find this is equal to 7440.97 angle of 4.05. It's exactly the same angle that we got, but of course, because you are referring to different size, now the voltage is different. Now here is the beauty. Let's find the voltage regulation, which is again, it's the V no load minus the V full load divided by the V full load. Now the V full load is the secondary voltage, which is this 7,200. And the no load voltage is the primary voltage, but the primary voltage referred to the secondary side, which is VB over A, which is that 7440.97 times 100. This will give me exactly the same terms, the same voltage ratio, 3.35%. Okay, so it doesn't really matter which model you use, you will get exactly the same voltage regulation. And if you want to find the efficiency, again, you will find the same value. The last part, what is the value of the core loss from an open circuit? What would be, if you have the model, what would be the value? So basically we will use, now we'll use the two models actually, and we'll show that we'll give you exactly the same value. So we have here RC, we have XM. Okay, now I don't care about this value because the core loss is represented in RC. So the voltage here is either V primary or V primary over A. Okay, so the P loss is equal to either the VB square divided by the RC, I would say RC1, or VB over A square, again divided by RC2. So if you use the first one, which will be referred to the primary, so it will be the 248 volt. This is the one that we got in the first part, square divided by RC, which is the 83.3, which is exactly the resistance that we calculated, which is approximately equal to 738.4.5 watt, and or it is equal to the 744.0.97. That is the value that we found in the second part or the second model, divided by the RC from the second model, which is the 75 kilo ohm. Again, you will get exactly the same value of the losses. So this is a nice, interesting question, but as I said, it has some error in the question.